Hello everyone. So now since you are here, it means you already have a knowledge of design of water distribution network. You have learned how to design a network, and if you have not, then you can watch this course from the playlist section. So as a designer now you can size pipes and you can guarantee pressure and flow to every customer that you are catering to. But let me ask you one thing. Are your designs good? I'm not saying that good as in functional good, but is it good as in an optimal good? Every meter of pipe, every pumping station, every single valve has a price tag attached to it. So if you size just one pipe, maybe a 50 millimeters larger than necessary, simply because you are playing safe, then you have committed a municipality millions in unnecessary capital expenditure and higher operational costs over the system's entire design period. So the problem is that traditional design is a trap, and we can see this with this simple example, which is known as the two pipe dilemma. Now we have a source, a demand node, and two pipes. We need to select the optimal diameter that combines from a handful of options. Let's say that 100 millimeter, 200 millimeter, 300 millimeter, to meet our minimum pressure requirements, let's say 20 meters. Now your initial guess is that maybe design X gives you a acceptable pressure at a cost of $120,000. But who knows that you could satisfy your pressure condition using a completely different mix combination of pipes, a mix you would never think of from your own. This is important because the difference between your safe design and the optimal design is tens of thousands of dollars, right? So if in a small network you think it is a small problem, then in a real city network the difference will be in millions. So the problem is too complex for a trial and error kind of solution, and finding that single optimal solution requires a completely new set of skills. So this course takes you past from the trap of manual design to the optimization imperative, right? I'll be teaching you how to systematically minimize cost, maximize reliability, and minimize energy simultaneously. How? Maybe with the power of AI. Now, to solve the optimization problem, we need to stop thinking about feasibility and start thinking about formalizing the research. What does it mean? It means that we must translate our engineering challenge into the language of mathematics and computers. So we define these three core elements: the decision variable, the objective function, and the constraints. Now, I am defining some new terms, and I will be subsequently defining some more terms in this lecture. You may get stumbled upon some of these terms, so don't worry, just bear with me and we will learn about each of these terms in the upcoming lectures. For now, we can say that the decision variables are the things that we have the power to change. For example, in our common water distribution problem, this can be the pipe diameter, or if we have a pump, then we can choose what kind of pump we are going to use, or if it's about operational parameters, then we can schedule things like start, stop, or the times, number of times. So these are the levers that we will be pulling time to time to change our outcomes. So these are decision variables. The next, that is the objective function. This is the goal which we want our system to achieve. Almost in any water distribution network, we want to minimize the total cost, because this is the most crucial thing. The total cost includes the initial capital cost and the operational cost. And finally, we put on the constraints. Now, these are the non-negotiables, right? These are the rules that define a feasible solution. The two major constraints you already know are hydraulic constraints and service constraints. The hydraulic constraints will be the mass and energy, which must balance, which the softwares like EPANET, water gems, etc. handles for us. And then the service constraints, that is the pressure at every node must be greater than or equal to the minimum required pressure. And any solution that violates this is simply discarded because it's infeasible. Now you may be thinking that if a problem is so clearly defined by math, why can't we just use the Excel solver or a simple calculus based method like the... Then I must tell you that the answer lies in the harsh reality of engineering. The classical solvers require the optimization surface to be smooth or continuous. Okay, so if your cost function changed smoothly like a hill, the programming methods could find the bottom of the valley. But engineers don't buy pipes in infinite sizes. We buy discrete commercial sizes which are available in the market, like 100 mm, 150 mm, 200 mm. So this makes the function stepped and discontinuous, right? For example, if a solver might want a 183 millimeter pipe, but since that does not exist, it has to choose either 150 or 200. And every time it hits one of these steps, the solver's logics break down. Further, for even a smaller network, say 50 pipes with 10 size options, you have multiple possible designs. And this is the curse of dimensionality. No traditional solver can check every single combination, right? So what did we learn? That classical methods get stuck in local minimums, and they cannot handle discrete commercial pipe size, right? So we need a solution that can intelligently jump across that stepped landscape and find the best global solution without checking every single option. Sometimes the solution is borrowed from the most efficient optimization engines we know, that is the nature. We use meta-heuristic algorithms. We will learn more about this in the upcoming lectures. It is an intelligent search technique based on the principle like evolution, how the humans evolved, or the swarms, or the ant behavior, to find a near optimal solution without exhaustive checking. They are designed to explore that stepped massive landscape. In this course, you will also master the king of these methods, the genetic algorithm. The genetic algorithm treats each design as a chromosome. A genetic algorithm treats each design option as a chromosome. It selects the best performing designs and then combines them through crossover and randomly changes parts through mutations. Over thousands of generations, the designs naturally evolve towards the lowest cost and the most robust configuration. You must have learned these examples, that why the necks of giraffe are long. Okay, so a person who is into genetics will answer that the longer necks were needed in order to reach the food that they want or to serve a certain purpose. Therefore, in multiple generations time, the neck of a giraffe gradually evolved. Now we also know why the cactus in desert have no leaves. They have evolved genetically towards the most optimum configuration. And it's not just about genetic algorithm. We will also use machine learning to create surrogate models using AI to predict EPANET results or water gems results in fraction of seconds and speeding up our optimization from hours to minutes. Crucially, we will integrate powerful AI platforms like ChatGPT, Gemini, Grok, and others directly into our workflow. We will teach you the exact prompts to ask Gemini or any other large language model to instantly summarize complex APANET reports or to debug your Python scripts and analyze sensor data for anomalies. Now you have seen the scale of the challenge. You are about to move from a skilled modeler to an elite optimizer who can deliver real, measurable, multi-dollar value. In the next lecture, we are going hands-on. We will formally define the maths behind the cost function and prepare our first Python environment. If you want the lecture 1 takeaway sheet and the 2-pipe dilemma APANET file flow, you can check the description link. If you want to access this complete course, you can simply go to our playlist section and then you have to choose optimization of water distribution networks and follow the instructions as prompted. If you have any queries which are non-technical in nature related to the course and its delivery, you can put your query in the comment section. I'll see you next time as we dive into the maths and the code. Thanks for watching.